All right, now let's see what is the third approach for fixing the heteroskedasticity problem. Okay, let me quickly go back to the whiteboard and remind you of the case, of the idea for the third approach. So in the third approach, we have to see, let me use black. You have to see if we know the functional form for heteroskedasticity or not, right? And if you're wondering, how is that possible that I know the exact form of the formula for the heteroskedasticity? And I can remind you, actually, for chapter 7, in the very last part, we talked about linear probability model, right? Do you remember linear probability model? When the left-hand side was binary, it was 0, 1, and the right-hand side was something. So for example, it was pass or fail. You pass the exam or fail, right? Pass the course or fail the course, something like that. 0, 1, you get your loan application get accepted or rejected. In finance, buy or sell, right? We talked about one of the caveats of LPM in the previous class, and we said the variance of u given x, by construction, it's going to be px multiply 1 minus px, and px was the probability of success, right? Because this is a Bernoulli function, and we know that what is the variance for Bernoulli, and it's px multiply 1 minus px. And so basically we know for a fact that the variance of u given x in linear probability model is a function of x. So it is heteroscedastic by nature, right? So we have to do something about it. So that's the bad news. The good news is that we know the exact form of heteroskedasticity. I know this function. I exactly know what is this function, right? So if I know the functional form, we're going to go ahead and use GLS, or weighted least square. GLS stands for generalized least square, and weighted least square is a special case for that, right? Then if we don't know the functional form, we're going to use FGLS. So on this slide, we're going to start with the case that we know the functional form. So so let me write it. So actually we have it here. So h of x is known. When h of x is known, we're going to use weighted least square. And we'll see what does that weighted least square is going to do. So heteroskedasticity is known, and it's up to a multiplicative constant. So basically, it's a constant multiply some function. And guys, remember this h of x must be positive. Why it must be positive? Because the variance is always a positive number, right? Sigma square is positive, so this h of x must be positive. So not surprisingly that it must be positive. Okay. Now, what is the idea here? The idea is that we're going to give smaller weights to the observation with larger variance. Okay, so let me actually use a whiteboard because this requires a little bit of more explanation. Now I'm going to go ahead and change the entire engine, right? So imagine this is my data set. I have a bunch of observations here, and then I have a couple of outliers there. If I use OLS, OLS is going to, well, let me actually be a little bit more exaggerated, put them here. OLS is going to do a fitted line, and that fitted line is how OLS pick the fitted line is basically look at the residuals and square them and etc., right? So we've talked about minimizing the soft score of residuals, right? So this is how OLS is doing the job. And as you can see, OLS is going to give the same weight. So this observation is as important as this observation, as important as this observation, as important as this observation, right? And OLS is going to be unbiased and etc., right? However, we're going to argue that, so I could have used another engine, and in that another engine was designed in such a way that, okay, let me go back. It's going to underestimate these observations. So if I have outliers in the model, basically, if I have some observations that the variance is higher, so maybe I have a bunch of them like this, the variance is higher, then weighted least square is going to underweight them, give them less weight because the variance is higher. If that's the case, weighted least square is going to somehow ignore them and maybe do something like this. So this is going to be my weighted least square. And as you can see, if we ignore these outliers, so weighted least square is going to be a better estimator compared to OLS. So that's the idea. Weighted least square is going to give less weight to the observation that their variance is higher. So why does that help us with the heteroskedasticity thing? Guys, remember, you know, for the heteroskedasticity, we were talking about wage versus education, right? So we know that the variance of wage is going to increase with the education. So if I use weighted least square, it's going to give these observations less weight compared to this, compared to this, compared to this, right? So this is how the weighted least square is due to fit a line for you, right? And mathematically, we're going to prove that how it is fixing the heteroskedasticity very beautifully. Okay, so that's the idea. I hope that you get the idea. Now let's see mathematically how does it do the job. Okay, this is our ordinary regression, right? So we're regressing y on, let's say, x1, x2, up to xk. The subscript I are just number of observations, right? So I can do y versus x1, x2, or yi, x1, xi1, xi2, and etc. Okay, we are going to say that, so this is how the weighted least square is taking care of the heteroskedasticity. Because I know the functional form of h of x, this is known. Because I know the functional form of h of x, I'm going to divide everything on the right hand side and left hand side by square root of h of x. We'll talk about it, why square root of h of x, but let's go ahead and do that. So we're going to go ahead and do that. Divide everything by square root of h of x, right? Guys, remember h of x is, so here we say h subscript I, so that's for a specific observation. It is known, it's a number. So you can go ahead and divide all the numbers that you have in the model by some other positive number, okay? And we can give them new names, so just call them star. So this is y star, x1 star, xi 0 star, basically that's your intercept, x1 star, x2 star, and xk star, right? The idea is that this transformed model, so this is a new model, this transform model is going to be homoskedastic. So why? I want you to think about it. So let me actually walk you through to the proof, and you will see mathematically why we needed to divide everything by the square root of h of x originally, right? So I'm claiming that this model, this new model, is going to be homoskedastic. So what does that mean? It means that if you do the variance of u star given x, it's going to be constant. Let's see if that's the case or not. So let's open it up. Variance of u star. What is u star? Guys, remember, this is my u star. It's going to be u divided by square root of h given x. So now use the properties of variance. Variance of u given x, multiply a constant. So that constant is going to come out to the power of 2. Then variance of u given x. So I can say 1 divided by h, right? So I'm doing this. Multiply the variance of u given x. Now, guys, what is variance of u given x? So I have it. So it's going to be, I have 1 over h, multiply variance of u given x, sigma square, h of x. Now, because h is positive, I can cancel out these numbers. So what I get? Sigma square. Voila. That's how magically this transformation did the job for us. That was tricky. It was smart by dividing everything by square root of h of x. But now I know why I had to divide them by square root of h, because it's going to be squared at the end of the day, and then the variance of this thing, u star given x, is going to be constant. It is homoskedastic. Again, you don't need to, well, I never expect you to do these kind of proofs for the exam or homework, but I hope that you understand how this weighted least square, by weighting them. So these are the new weights, right? So I'm giving new weights to the observations. If the variance is larger, can you see that? If h of x is larger, the weight is going to be smaller. This is exactly what we did here. If the variance is larger, the weight is going to be smaller. So this is what the WLS is doing, right? So again, these beta stars, these are examples of GLS, generalized least square. In this example, well, but here, because the weights were inverse of the variance, we call them weighted least square. Okay. So if the other Gauss-Markov assumptions hold as well, then weighted least square is best linear unbiased estimator. Now, going back to the whiteboard, Do you remember that? We say if we have heteroskedasticity, OLS is not going to be best anymore. We know that weighted least square, or GLS, is going to be best. Best, it means that it has the smallest variance. All right, so that was the third approach, right? Let's look at an example for the third approach. So what is the example? The example was our, let's say, linear probability model. We knew the exact form of heteroskedasticity. So as I said, it's going to be called px multiply 1 minus px. And what is px? P is the probability of success. Basically, it's my y hat. Again, if you recall from our linear probability model class, y hat is a probability, let's say 40%. So the probability of passing the course, 40%. The probability of, I don't know, getting the loan, 70%. The probability of buy, 10%, and etc. These are probabilities, right? And so if I do y hat multiply 1 minus y hat, this is my h of x. So I do have h. So I can now go ahead and use weighted, calculate all those beta stars, the weighted least square beta stars. And then for a fact, I know that that model, that new model, is not suffering from heteroskedasticity because we've mathematically proved it. Okay. So what are the steps in R? Again, guys, this chapter in general, the application in R cannot be easier. It cannot go wrong. There is no tricky question here. It's like mathematics. 2 plus 2 is 4. There is no tricky part. There is no strange interpretation or trick interpretation. It's very straightforward in that sense. Okay, so there are some algorithms. You just stick to the steps and then you do the process. It's very straightforward. So what are the steps? Estimate the model by OLS and save defeated values, your y hat. Why? Because I need the y hat to construct the h. Okay, so that's step number 1. Step number 2, determine whether all the fitted values, the y hats, are inside the unit interval. They're between 0 and 1. Why do I care? Because, guys, remember, y hats are probabilities in this model. So if the probability cannot be negative or it cannot be greater than 100%, right? So you test that. If all the y hats are between 0 and 1, yeah, that's fine. Go ahead, go to step 3. If not, we have to make some adjustments. What are the adjustments? We're going to say, okay, if y hat is less than 0, just replace them with 0. If y hat, or drop them from the model. If y hat is greater than 1, just drop them from the model or just replace them with 1, right? And usually the number of observations that the probabilities are less than 0 or greater than 1 by the model, hopefully they're less than 1% from the entire data set. If 50% of the data, if the predictions are negative, probabilities are greater than 1, so this model is not good. Linear probability model, you should not even think about it, right? But the ones that we have in the course are designed in such a way that you can still use linear probability model, okay? Then we go to step 3. Step 3 is constructing our h. These are the weights. So h is going to be y hat multiply 1 minus y hat. And then finally, we're going to run this regression by the new weights. So this part is very easy, and we call them weighted least square in R. So let's see how we can do it in R. Imagine, so here's an example. Imagine we want to regress PC ownership. So this can be 0, 1, right? 0, 1. On high school GPA, ACT score, and this is parents' college. So basically, parents' college is a binary indicator equal to unity. It's 1 if at least one parent is college educated, right? So if father goes to college or mother goes to college, so this pair college or parents' college is going to be equal to 1. Otherwise, it's going to be equal to 0. Okay. Okay, let's run that regression. Again, remember the numbers in parentheses are the ordinary standard errors. The numbers in brackets are the robust standard errors, right? So these are the numbers that are reported. However, we're not going to use the robust standard errors in this example. We're going to use the third approach, weighted least square. Weighted least square, I know that if I look at the standard errors of weighted least square, they're not suffering from heteroskedasticity. That's fine. Okay. All right. Let's see how do we do that in R. And by the way, in this example, because all of the OLS fitted values, the y hats, are between 0 and 1, we don't need to do anything. I'll give an example in the class that the y hats are not between 0 and 1, so then you have to fix them. Basically, again, you can either drop them or replace the negative ones with 0, positive greater than ones with 1. Okay, so what are the steps in R? Again, run your ordinary regression, call it whatever. We called it MRM, dummy dependent. Again, this is a name, you can call it anything. Then save the predicted value. So this is my y hat. So this is your y hat. Then look at the range of the y hat. And because the range of the y hat in this example is fine, it's between 0 and 1, we go to the third step. You construct your weights to h hats. So h hat is going to be y hat multiply 1 minus y hat. And then finally, so these are the weights. The weights are going to be inverse of those, so 1 over h. Then, how do we do it in R? In terms of weighted least square? Let's just call it weighted least square. Again, this is a name. So LM is LM. We have seen this before. So far, it's exactly like OLS. The only difference is that we're going to say, okay, PC on high school GPA, ACT. This is the only difference. The weights are not the default weights. We are going to give them new weights. And the weights are inverse of the variance. Right? So, and then, so here's the part that's is going to distinguish our OLS from the new engine, which is weighted least square, right? And then you pass the data. Okay, so this is my OLS, this is my weighted least square. And of course, guys, the coefficients are going to be different because going back to this whiteboard, look at that, this slope is different. The slope for OLS is the slope for the weighted least square. Maybe something like this. The slopes are different, intercept is different, and etc. Right? So these numbers are going to be different, and of course the standard errors are going to be different as well. Right? So which one should I trust in terms of number of stars and etc.? This model, weighted least square, because this model, this regression model, by nature is heteroskedastic. We are using linear probability model. The dependent variable is 0, 1. So there is no way that this model is going to be homoscedastic. Right? So for that reason, we have to go ahead and use weighted least square. Here's a question for you. I'm going to answer this question in the class, but just to give you some food for thoughts. So just think about it. How do you construct the heteroskedastic corrected standard errors? So basically I'm asking, do you remember this is a third remedy? Use the second remedy. So just how do you construct these numbers? Because guys, either way is correct, right? So you can, let me see, can we do number 1, the first remedy here? Can I use log? See here, log doesn't make any sense, right? Because PC is 0, 1, it doesn't make sense. First of all, I cannot take log of 0, it's minus infinity. So I cannot do that's ruled out. I cannot use log transformation. So I can either use second remedy. So remember, what was second remedy? OLS plus robust standard errors. Or the third one, which is weighted least square. This is what we did here. And I'm going to give you a question at home, give it a try, how we can construct the robust standard errors, OLS plus robust standard errors. It's not complicated, we did it here. So we did it here. It's going to be exactly the same. Just give it a try. All right. Now, as for the final couple of slides, I want to talk about feasible GLS. Okay. This feasible GLS is going to be non-testable. I'm not going to test you on that. And I think it doesn't even show up on the homework as well. But for your final project, if there is a group there that your model is heteroskedastic and you do not know the functional form of h of x, then you have to use FGLS. Okay, so in this couple of slides, I tell you how to do it in R. In the classroom, I will give you an example of how to do it in R, but again, this is not testable. And with 99.9% probability, none of the projects that you guys are going to work with requires FGLS. Okay, but if it did, just let me know. We're gonna go over the FGLS. I'll make sure that I double check your code, or you can discuss it with me or the TAs. Just make sure that you know how to do it in R, right? Okay, so now if the heteroskedasticity function is not known, that h of x is not known, we have to estimate that, right? So basically we have to come up with the estimated version of the h of x, right? So let's see. This yields an estimator called the feasible GLS or FGLS. Then the resulting FGLS estimator is no longer unbiased. but it is consistent and asymptotically efficient. It's like when we discussed the variance of the I think it was in this slide that the variance itself was not unbiased. Where was it? So here, the robust standard errors are not are biased, but in large samples are going to be unbiased, but they're more efficient. Same story here. So FGLS, again, these estimators are the estimators themselves are no longer unbiased, but they're consistent and asymptotically efficient. Right? Basically, if the sample size is large enough, you don't need to be worried about the FGLS estimator. Okay, so let's see what is this h of x that we don't know, right? So if you don't know a functional form, you have to make some assumptions, right? This is economics or econometrics. We live in a world with lots of assumptions, right? So there are many ways to model this heteroskedasticity function, but a fairly flexible approach is this one. We're going to say that the variance of u given x is equal to this. And guys, remember, this is an assumption. We say it's a number, multiply e to the power of, so this is exponential, e to the power of a linear function of explanatory variables. Okay. And then from here, we can, so for example, I can say, so please remember, this is e to the power of something. So if I take the log of u hat squared, so basically it's going to be, so if I take the log from both sides, log of e to the power of something, it's going to be equal to that something. So here's what we get. So the log of u squared is going to be that thing on the right. Right? Again, don't be worried about all these derivation, etc. The application in R is easy, and that's it. And again, the odds that you're going to need it for your final project is very, very small. I just leave it there, and at least in order to be comprehensive in terms of what are the options for the remedies, I just leave it there, but it's not testable. Okay. So how do we do it in R? So we first run the regression. This is our simple regression, y on all the x's. Save the residual. Then I have to construct the log of u hat squares. And then I have to run this regression, log of u squared, on the linear function of x's. And we save the fitted values, we call them g hat. Then we calculate the weights. If I take the exponential version of the g hat, I'll come back with the weights. And then I'm done. I have the weights, and that's it. So we're going to use the LM function, blah, blah, blah. And the weights are the one that we just defined. So h hat. H hats are going to be the weights. Well, actually, it's going to be 1 over h hat. So we just call it w, and w is defined as 1 over h hat. All right, so these are the weights. Okay, so that's pretty much it. Again, I'll go over one example in the class in R. So you know, again, for the groups that are dealing with heteroskedasticity, that the functional form is unknown, you know how to do it in R. For the exam purposes, this is not testable, but it is good to know that what is FGLS and what is it trying to do. Okay, all right. So let's sum up what we had. So let me actually go over the whiteboard again. I know it's messy, but I hope that you can see the big picture. This is your final project. You start from here. Simply run the BP test. If you fail to reject the null, it's homoskedastic, you're done. That's it. If you reject the null, it's heteroskedastic, you have to do either this, this, or this. Okay, that's it. I hope that you enjoyed chapter 8. I know it was a little challenging, but in terms of application, as I said multiple times during the lecture, it cannot go wrong. There's nothing tricky in this chapter. You just follow the rules and you don't need to memorize anything, right? All right, I will see you in class. Until then, take care.